on these primaries of the coset theory, and this is identified with V plus R A minus 2 minus L. Now, this identification is going to be important for the actual computation of the scattering amplitudes for the following reason. So, on the cigar, there is no conserved winding. Okay, so, so generally, a scattering of the string modes on the cigar. So even though when these operators are constructed descending from SL2 W0 model, there are these momentum winding number, but the winding number will not be conserved. However, how do you actually calculate correlators of these vertex operators, which is necessary for computing string amplitude? The most straightforward class of correlator that you can calculate are the ones that conserve momentum and winding. Because for those class of operators, you can say that if you're interested in computing some VV, say 4-point function, you can just calculate this phi 4-point function in the SL2 theory, and then divide by some free boson correlator in this U1, this X bar. So this works for the winding number conserving correlators, but for the winding number non-conserving correlators, left-hand side will be non-zero, non-trivial, but right-hand side will be 0 divided by 0. So the winding number non-conserving correlators cannot be calculated directly from the mother theory in this coset construction, and those are actually very complicated. In general, the 4-point function is not known explicitly, and you have to, in principle, compute higher point function of the winding number conserving correlator, higher point correlators, and kind of then try to factorize and extract from that the winding number non-conserving correlators, which is generally very complicated. It's not known at level of 4-point function. And we'll avoid dealing with those. We'll restrict ourselves for now to just the winding number conserving correlators. A class of winding number conserving correlators would be the following. So let's say so for example, let's consider V plus Ramon L1, V plus RR L2, V minus RR L3, and V minus RR L4 with say this L1 plus L2 minus L3 minus L4 equal to 0. This is a winding number conserving correlator. We'll in fact further, in actual computation, we'll reduce to some further special case where I take L1, L2 to be the same, and L3, L4 to also be the same L. So this will correspond to a sort of particular choice of a set of color polarization of these U1 to the K minus 1 gauge bosons. Okay. So how does one actually go and calculate the correlators? So our strategy is that for the winding number conserving correlators of the cigar coset, you can calculate this from the SL2 W0 model and primary correlator and divide by the free boson part, which is pretty trivial. But this is still actually fairly complicated. And in fact, so you can write down these correlators of some phi J1, phi J, I'm omitting the M in M bar, phi J2, phi J3, phi J4 in SL2 theory. But as I mentioned, the actual, so these for general real values of J describe non-normalizable vertex operators. So in order to get these normalizable vertex operators, you have to take a limit of these J approaching, Ji approaching some special value, say Li over 2, sorry, over here, J is L over 2, and L is an integer here. So you start with some generic real values of J, you can calculate this correlator, and then you take this limit. In this limit, the SL2 primary actually blows up, and you have to extract the residue, and so there's some coefficient of the pole in that limit. So schematically, I write I from 1 to 4, J I minus Li over 2, and then you're left with some correlator that is finite, and that is the correlator of these localized vertex operated at the tip of the cigar. So that's a procedure that one would use to calculate this 4-point function. But then how do we calculate this? This is also not known in general. So to do this, we have to, so these correlates in principle can be calculated. So in the counterpart of SU2 mod U1, so these things are usually determined through the Nishnik Samologikov equations. And here one can also write down these Nishnik Samologikov equations. Actually, in this case, these KZ equations do not quite a priori fix. It's not easy to fix the solution of the KZ equations. What one can do, this was shown by Ribot and Teschner, is that you can, the KZ equations, which are a set of differential equations for, actually I erased that, for this phi j. So remember I packaged this phi j and bar with definite j3 and j3 bar quantum number. I repackaged this into this generating operator phi j x z, which has now some nice interpretation in this wave function in Euclidean ADS3. So these correlators of these phi j, x, z, etc. So these are based on KZ equation, which is a set of first order differential equation in z and second order differential equation in x. One can show, so this equation will be fixed by the singularity of the endpoint function as the zi as the z's approach one another. So some z1 approach z2, you will be able to relate. So the singularities as two of these operators approach one another to some lower point correlator. And then you get some kind of recursive kind of boundary condition for these endpoint functions, general endpoint functions in this SL2 W0 model. Now that still sounds horribly complicated, and it is. But Ribot and Teschner were able to prove that there is a relation that actually allows you, by noting that two quantities that solve the same equation, then you know they're the same. They were able to show that the endpoint function of the primaries in SL2 W0 model can be expressed as an integral of a 2n minus 2-point function in Liouville theory. And that's a relation we're going to use to determine these 4-point functions. So let me describe that relation. So I mean, this is kind of a technical step that would not have been, I mean, if we didn't know this, it would have been extremely difficult to calculate the correlates of interest. But thanks to this, we're able to re-express this in terms of some known correlation functions. So let me describe the relation. Ribot and Teschner, I think this is Teschner, 2005, show that the endpoint function of the phi j's in the SL2 W0 model, these are related to 2n minus 2 point function in Liouville theory. What is this relation? It says that, so for our interest, the fermion part is just some free fermion, we can handle that. The bosonic part, which is the bosonic SL2 at level k plus 2. So this will be related to some Liouville theory. So the Liouville theory regards some action partial phi squared plus mu e to the 2b phi, the well-known extremely important conformal field theory. This guy has central charge 1 plus 6q squared where Q is B plus 1 over B, the background charge of the UVL field. This is the theory of central charge 3 times K plus 2 over K. These are not the same CFT. Okay, so in fact, for the correspondence to work, the identification is that 1 over K is going to be identified with B squared. So these are not the same CFTs, even the central charge do not agree. But the statement is there's a relation among the correlators. So here we're going to be interested in these phi, j, and bar with dimension minus j plus 1 over k. In the Newville theory, we're going to be interested in vertex operators of the form e to the 2 alpha phi, and these things have dimension alpha times q minus alpha. And the correspondence, roughly, is the following. The correspondence says that the endpoint function of phi j from 1 to n at some position zi bar is going to be expressed in terms of there's some prefactor that depends on the z's, some integration of some coordinate ya. There's some function involving the z's and y's. There's some differences of the coordinates, absolute value to some power. I won't write down all of this expression. Times now the 2n minus 2 point function in the Newville theory, which is product I from 1 to n, v alpha I at the position zi, and a from 1 to n minus 2, v minus 1 over 2b ya bar. So this is a 2n minus 2 point correlator. So I haven't told you what these alpha i's are. So the alpha i's, so this, given this ji, sorry, this will be I from 1 to this ji. Okay. And there's a correspondence between alpha I and ji. The formula is that alpha I is going to be equal to minus b ji plus 1 over 2b. So this is a dictionary that allows you to relate endpoint function in SL2 to 2n minus 2 point function in Newville theory. So here, let's say for the 4 point function on this side, we're going to relate this to 6 point function in Newville theory with these v alphas, v alpha 1, v alpha 2, v alpha 3, v alpha 4, and then two other operator, this v minus 1 over 2b, v minus 1 over 2b, and integrate over the position of these two vertex operators. Okay, so this sounds pretty complicated, and how will we go about and calculate this? Now, it turns out that the way that allows us to actually calculate is that we don't need to know this full correlator for general j's. We're interested in extracting this limit as j approach these special discrete set of values, and we want to extract the residue as j approach those values. It turns out that for this kind of operator of interest with this assignment of plus, plus, minus, minus, it turns out something nice happened. One recognized that in this case, it turns out that the pole in J3 and J4, so pole in J3 and J4, the poles come from the prefactor in this formula of Ribot and Teschner, whereas the poles in J1 and J2 come from the limit in this integral over the y variables, where these two vertex operators approach v alpha 1 and v alpha 2. So then one only needs to extract some limit of the 6-point function as these two vertex operators approach these two vertex operators. Now, if you have studied Newville theory, you will know that v minus 1 over 2b is a kind of important vertex operator in Newville theory. Formally has negative for real b, positive b. This b minus 2b has negative conformal weight. It's a degenerate primary. So v minus 2b this is a degenerate primary with the null state, if you're a serial descendant, the null state at level 2. So all the correlating functions of involving v minus 1 over 2b actually can be determined in a way that's not so terribly complicated. In general, if you take two operators, look at the OPE in Liouville theory, there will be a continuous family of primers that appear in the OPE. But if you take an OPE of a general operator V alpha with a degenerate primary, then there's only a finite set of operators that appear, primers that appear in the OPE. That is the case for this V minus 1 over 2B. If you take this OPE, only two of the operators appear, and then you can reduce the problem to computing some 4-point function in Liouville theory.
So in the original version of Liouville-Teschner correspondence, the right-hand side, the y is fixed, determined as a function of the quantum numbers of the operator phi. I thought.
No, there's an integration here. There's the y is being integrated. There's some kernel and the y is being integrated. That's the relation.
Oh, I see.
Yeah, I think maybe there are different versions of the formula, but here.
So you have integrated over some quantum numbers of phi?
No, quantum number phi. No, quantum number phi are.
Phi depends on j.
This depends on m and n bar. I didn't write the dependence, but this is also included on the right hand side.
Oh,
yeah, sorry. Yeah. So I can't really write all the details out on the board. There's just there's way too much to write, but you can look at details in our paper. So in any case, the problem now is reduced to computing this 4-point function in Liouville theory, essentially, which, once again, for the class of operators of interest, do not have closed form expression. So, but we're not afraid of that in Liouville theory, because we know the 3-point function at least. We know the 2-point and 3-point function in Liouville theory. And the 4-point function can be obtained by integrating these with conformal blocks. And that's what we do. Liouville theory, let's say, actually this is the Liouville direction. There's potential e to the 2b phi. So in Liouville theory, if you look at vertex number v e to the 2 alpha phi, there are, usually people discuss two types of vertex operators. See, if you take the conformal weight, so conformal weight is alpha times q minus alpha, just like in SL2, for Liouville theory, if you want conformal dimension to be real, you need to say either alpha is q over 2 plus an imaginary number, which corresponds to some scattering mode, some wave coming in, scattered back out, or alpha is real. Now, in Liouville theory, of course, if alpha is real, in the first case, this describes some scattering wave that has natural physical interpretation for the Liouville theory on the circle. In this case, these are not really good vertex operators because they are not normalizable. But is this not non-normalizable vertex operators? I mean, they still have well-defined correlation functions, and it's those that will enter this commutation of SL2 correlators of interest. But the standard kind of conformal block decomposition actually works on this basis. So these actually should be regarded as the set of operators in the Hilbert space of Liouville theory, whereas this should be thought of coming from this by analytic continuation. So we'll focus on these guys. If you look at 4-point function Liouville theory, of this alpha 1, alpha 2, alpha 3, alpha 4, you can write this as just write this pictorially, integration over some intermediate channel, I write like this, alpha 1, alpha 2, alpha 3, alpha 4. Intermediate channel will be labeled by some other primary alpha. This integration is along the contour q over 2 plus the imaginary axis. And what I write here, this is basically, what this means is that I take the 3-point function alpha 1, alpha 2 with alpha, and 3-point function alpha 3, alpha 4 of alpha, and then times the conformal block f, which depends on this alpha I, also depends on alpha, and then depends on the cross ratio, I call it z of these 4 points, and then there's some prefactor that's some standard function of the zi minus zj to some power. These three coefficients are known. They are pretty complicated, and we need all the details there, actually. So these are expressed in terms of Barnes double gamma functions. Are worked out by various Zamlachkovs and by Teschner, and very hardworking people. These conformal blocks, as you might know, also come very complicated functions. They don't have generally closed form expressions. One can write down some series expansion for these, and since we do not have any closed form expression available, we have to work with the series expansion. So that's what we do. And this series expansion, so I won't even try to write down this formula on the board because it'll take me probably 1 to 5 minutes just to write down that formula, the recursion formula of Zamlachkov's. But I can use, so the B Zamlachkov, AL Zamlachkov, back in the late 80s, discovered some powerful recursion formula, for these conformal blocks. So those formula looks fairly horrendous as an analytic formula, but numerically they allow you to do efficient computations of these conformal blocks, and that's what we do. And then you have to integrate that along this alpha. After the integration, you get some function of the cross ratio, and for the string theory computation, eventually you have to integrate over also over the cross ratio. Both steps will be done numerically, so that's the computation we do. Now, I'll just point out one subtlety in this computation, which has to do with this analytic continuation. This subtlety was pointed out by Malacina and Uguri in the study of string theory in ADS3, which is that, so in the alpha plane, the contour is along this q over 2 plus imaginary number. That works if alpha 1, alpha 2, alpha 3, alpha 4 also lie on that contour. That was the definition. That was how the conformal block decomposition is supposed to work. In fact, it was completely miraculous that that formula obeys crossing symmetry. Okay. But if you take the alphas off the axis, generally you will not obey crossing. So you have to be very careful. You have to do the careful analytic continuation. In doing this analytic continuation of the alphas, alpha I starting over here, and continue to some real value, it could be that, this function has some zeros and poles, all of which are known from this Barnes double gamma function. You have to worry about the possibility that as you analytically continue alpha 1, alpha 2, for instance, there's a pole of this three-point coefficient that crosses this contour. When that happens, you have to deform the contour accordingly, or you have to keep track of that extra residue contribution. And if you don't keep track of that, you'll get an answer that makes no sense because it will be inconsistent with crossing symmetry. So that's also details that one needs to actually do this numerical computation. In most cases, well, in some simple cases, one does not have to worry about that, but we did encounter some situation where you have to worry about that, and after taking account of these residue contributions, one gets a consistent result. After all that work, one can write down the 4-point amplitude of these particular set of, let's say, Raman vertex operators in double-scaled little string theory, which is schematically of the form, this amplitude in double-scaled LST is going to be, there's going to be some integration in the cross ratio of some correlator of this Raman vertex operator V Raman L V L L matrix Raman here, so VL plus and VL minus VL minus. So one of them is put at position Z, the other one says say 0, 1, infinity, and one has to there's various insertions of the seagulls as one usually do, and after so let me just to summarize this computation is that you I guess I erased that formula for the vertex operator. So here these vertex operator, remember, this consists of some so this R1, 5 part, which is standard free field computation. Then there's the non-trivial part in SL2 mod U1 coset. And then there's the one part in SU2 mod U1 coset. The ZK orbital can be taken into account just by the careful assignment, and that has already been taken into account by careful assignment of the quantum numbers. So the SL2 mod U1 correlation function for the one number conserving correlators of the type that we calculated, that was related to Lugol forming function, which is written in terms of this component block, which one had to integrate numerically. The SU2 mod U1, this is a rational component field theory, so all in principle, one can solve these primaries explicitly. We did this computation explicitly in the case, in the case k equals 2, 3, 4, and 5. In this case, the SU2 k mod U1, this is the case n equals 2 minimum model, as I already mentioned. The k equals 2 case actually is trivial. Standard charge equals 0. This is a trivial theory. It's just identity operator. K equals 2 is a free boson theory. Has some radius 1 over square root of 3. You might know that's a supersymmetric. Well, that's equals to minimum model. K equals 4. The operators in this minimum model can be constructed by taking a free boson plus Ising model, plus the Ising model, and one needs to use the disorder operator in Ising model to construct the relevant primary that will enter this vertex operator. In the k equals 5 case, this involves one can construct the relevant vertex operators, the vertex operators of interest, by taking the free boson and combine with a primary in a three-state Potts model. This three-state Potts model is the center charge equals 4/5 minimum model, bosonic minimum model. So these are the inputs from the minimum model side. We take this correlation function from the minimum model, multiplied by the correlation function from this cigar coset, multiplied by the correlation function from the R115, and then we integrate over the cross ratio. So that's what we did, and then we get that integration can be done order. So in practice, you have some momentum dependence. So what we do is we do the alpha prime expansion. You can do this order by order, expanding alpha prime, and once you set this up, it takes some time to sort out all the errors, but the alpha prime expansion is actually fairly straightforward. So it doesn't cost as much effort to go to higher order in alpha prime once we have this. What does this tell us about the six-dimensional gauge theory? Okay, so the amplitude will be written. This is a string tree level, double scale Leo string theory, tree level amplitude. It has some alpha prime expansion, which let me write as A0 plus alpha prime A1 plus alpha prime squared A2 plus dot dot dot. Actually, my purpose, let me write this as A1, A2, A3, label it like this. As I mentioned last time, alpha prime, which is L string squared, will be identified with G on Mills squared in 6 dimension. So this alpha prime expansion, it would correspond to, at least on the face of it, loop expansion, the 6-dimensional gauge theory. So just computing the string tree of amplitude, you get some information about all loop answer in gauge theory. If that gauge theory is well defined. The string loop expansion, on the other hand, as I also mentioned last time, the string loop expansion G string squared will correspond to 1 over G on Mills squared MW squared. So it goes like 1 over the distance on the Coulomb branch squared. What this corresponds to on gauge theory side is that if you calculate some amplitude in the gauge theory, say some loop order,